Hello, this video is entitled The Dot Product, specifically the dot product for matrices. Now, up to this point, we've learned, some of the matrix operations. Um, how you can add and subtract matrices, and you can multiply a scalar, which was a number, times a matrix. We never talked about the idea of multiplying matrices together. And actually, there are two different types of multiplication. We just don't straight out say, find the product between two matrices. You have to define which product you're looking for. Right now, we're studying the dot product. Another section will be what's called the cross product. So the dot product is a type of multiplication between two vectors. It's very easy. The dot product will always yield a scalar result. So now they have the results here, whether you're dealing with a plane vector or a space vector, it's essentially the same thing. I'll just look at the space vector here, and that way, you can remove the extra term you don't need if you're doing a plane vector. But we say u dot v, so it's got a dot right there representing dot product multiplication. And if u is u1, u2, u3 are the components of u, and v1, v2, v3 are the components of v, your dot product is u1 times v1, right here, plus u2 times v2, right there, plus u3 times v3. So it's really that simple. Here's a couple of, now this one, of course, doesn't have a third component there, but so to find the dot product of the vector 2, negative 3 was 6, 1. 2 times 6 would be 12. Negative 3 times 1 is negative 3. 12 plus negative 3 would be 9. Now for this one, with 4, negative 2, 3, and 2, 5, negative 4, we take 4 times 2, which is 8. Negative 2 times 5, which is negative 10. 3 times negative 4 is negative 12. Add those three values up, and you'll get negative 14. So dot product can take on any real numerical value, positive, negative, 0. Not sure if I have this in writing anywhere in my notes, but let me, I might actually have it in the section on cross product, but I'll just say it now just in case. But there is no such thing as division of matrices. There will not be any kind of representation for dividing matrices. That is not a thing. So here are some properties of the dot product. U dot v equals v dot u, commutative. You have the distributive, which says u dot v plus w equals u dot v plus u dot w. Now I would like to mention, just because you have certain properties that are true, it doesn't mean you have to use that property. So let's say if I was using this number 2 right here, and I saw I'm going to take a vector and dot it with the sum of two other vectors, I would add those two vectors inside the parentheses first, and then just do one dot product. That would be the same thing. But you can do it either way. Okay, so a scalar multiple just kind of stays there with the dot product. So u dot v with some number multiplied in front. You can put the number wherever. You can multiply your dot product by that value. This one, the 0 vector. It's got to be a vector, not the number 0. The 0 vector dotted with any other vector v would be the number 0. So you can see the difference in this book where they use boldface to represent the vector, and that's the number 0. And any vector dotted with itself is the same thing as the magnitude squared, which I just did this for two variables here just to show you. So if you had v1, v2, dotted it with v1, v2, you'd have v1 times v1, which is v1 squared, and you have v2 times v2, which is v2 squared. So that's your result. Now over here, this is kind of disorganized a little bit, sorry about that. but the magnitude of v is the square root of v1 squared plus v2 squared. So if you square that magnitude, you get rid of the square root, and then it equals this result right here. So that's kind of sloppy looking, but that's all right. Now here's one used for what the dot product can give us. Finding the angle between two vectors. If theta is the angle between two vectors, non-zero vectors, u and v, and theta is being between 0 and pi, so it's always measuring the closest distance. In other words, automatically, this formula will do that. Let me just kind of do a rough sketch for you on a new page. Let's say you had a vector like this, and then we had another vector like this. The calculation in the formula is automatically going to measure this angle between them and not the angle all the way around like that. So it's automatically measuring the shortest angle, the one that's less than 180 degrees. And that formula says the cosine of that angle theta would equal u dot v divided by the magnitude of u times the magnitude of v. So therefore, if we're trying to find theta using trig inverse properties, theta would equal then cosine inverse of u dot v over the magnitude of u times the magnitude of v. So I guess this definition is given in is in radian form. I usually like to use degree form on my test. So just if it's asking degree, just make sure your calculator is in degree mode. There are some things in calculus where I like to get the radian answer, but this is one where I believe I prefer the degree answer better. So here's the angle between the vectors u and v. Now, granted, these are two space vectors, so what you're having to imagine is the two space vectors are then on the same plane they would fit on, and then we're measuring the angle that way. That's a little bit different than vectors in the plane, because vectors in the plane are automatically on the xy plane. This would just sit whatever plane those two vectors lie on. So it's pretty straightforward. So we just come down here. It doesn't matter what order. So I did what order you do this in, but I found the magnitude of u. So 2 squared is 4, 7 squared is 49, 3 squared is 9, square root of 62. And magnitude of v would be negative 1 squared, which is 1, negative 2 squared is 4. That gives you square root of 5. The dot product would be 2 times negative 1 is negative 2. 7 times 0 is 0. 3 times negative 2 is negative 6. You add those up and you get negative 8. And the angle, I just use 2 decimal places, obviously whatever requirement you use there. So it would be cosine inverse of the dot product, negative 8, over the square root of 62 times the square root of 5. Now be very careful when you put this in a calculator that you don't have to do them under the same radical like I did there, but you would definitely need to make sure you had them in parentheses, or some way to make sure you keep both those radicals in the denominator. Because if you just went negative 8 divided by the square root of 2 times the square root of 5 separately, all in those parentheses, it would think the square root of 5 was on top. But you see here, I just used radical properties and just put the two numbers together under the same square root, which worked. 117.02 degrees. Okay, I actually did. I didn't sketch the plane, but I used maple to sketch the two vectors and just kind of sort of drew you. I know it's hard to tell. Maybe I should do this graph again and change the angle around the view, because it almost looks like it's like 90 degrees, but it's tricky to see from this angle, so I didn't choose a very good view on this. So maybe if you're viewing this video later and I may have already changed the view, I'll probably leave this view in here, this one right here, and then put another picture in there next to it, and you can see what I'm talking about. So that way. Oh, all right. This needs to be rotated around a little bit because it doesn't look like it's more than 90 degrees, but it is. Now, let's see. Definition of orthogonal. Orthogonal, and this little clip right here, perpendicular. Orthogonal is just a term we use for vectors that kind of means perpendicular. It just means the same thing. Perpendicular, orthogonal, normal. They kind of mean the same thing. They're forming a right angle, 90 degrees. So here they're kind of saying, you say vectors are orthogonal. Two lines or planes are considered perpendicular. We'll talk about that later. And then we say a vector is normal to a given line or plane. So they're kind of interchangeable terms somewhat, but it just all means 90 degrees. But real straightforward. If u dot v equals 0, you can stop the process of trying to figure out your angle because it's automatically 90 degrees. In fact, you could put cosine of inverse in the calculator and you'd see it was 90 degrees. But so if you're trying to check, so a question asks you, are these two vectors orthogonal or not? All you have to do is do the dot product. If the answer is 0, the answer is yes. Anything other than 0, the answer is no. Now, in another video, we've talked about parallel. Parallel means the vectors are a common, one of them's a multiple of the other, whether it's a fractional multiple or a whole number multiple. That's how you know that they're parallel. So we have two vectors, and we're going to determine whether or not they're orthogonal, parallel, or neither. So they don't have to be orthogonal or parallel. If they don't meet those requirements, they default into neither. It doesn't really matter which one you check first. You can check parallel first. You can check orthogonal first. You don't check for neither, in other words. Okay, so I did this with this one, these two vectors, u and v. So I went ahead and tried to check for orthogonal first. I did the dot product between u and v, and I got negative 228, which of course is not 0. So I've eliminated orthogonal. So now it's either parallel or neither. And this is the way I did this in the other video, is just take a ratio. It doesn't matter which one you put on top or which one you put on bottom. Just be, you got to do it the same way every time. So if I'm putting v over u, I have to do v over u for all three numbers. So I chose that route. V, the first component, 6 divided by negative 4, is negative 3/2. So what we're looking for is all three of those need to be the same ratio for it to be parallel. Negative 9 divided by 6 is negative 3/2. Negative 15 divided by 10 is negative 3/2. So that means vector v is a multiple of vector u, negative 3/2. So therefore, we have two parallel vectors. That's not too bad. Let's look at this next one. These two vectors, u and v. Do the dot product, ends up being 0. Game over, orthogonal. Oftentimes, these problems will also ask, determine whether they're orthogonal, parallel, or neither, and it'll say if neither, find the angle between the two vectors. Parallel doesn't really have an angle between the two vectors, and orthogonal obviously is a no-brainer. It's 90 degrees. Now here's one that was in 2 space, so I could graph it a little easier for you to see without having to use technology. All right, negative 6, 7, 2, and 4. Here's the dot products, not 0. Did I actually put that? Yeah, I did put that in there. If neither, find the angle between the two vectors. Wasn't sure if that was in the instructions or not. So the dot product's not 0. You can quickly see that v is not a multiple of u, and then so that means it's neither. So let's figure out what the angle is between those two. Magnitude of u is square root of 85. Magnitude of v is the square root of 20. And then the dot product was 16, which we need. So the angle theta will be cosine inverse of the 16, the dot product, over those two square roots multiplied together. And notice once again, I put those two numbers under the same radical, made sure they stayed within the parentheses, so they're all part of that same square root. And I got 67.2 degrees roughly. That looks about right for that picture. 67.2. Let's see about this one. So here we have two vectors, two space vectors, u and v. Just moving some stuff around here. And you can look at the dot product. And the dot product is not 0. So it definitely rules out orthogonal. You dot u and v, 2 times 7 is 14, 3 times negative 1 is negative 3, negative 5 times 4 is negative 20. We have negative 9. And then you can see that real quickly, if you do those ratios, you've got first one's 7 over 2, and then you have negative 1 over 3. So right there, that takes care of they're not scalar multiple of each other, so it's not parallel. So we definitely have a neither. I guess I should have. I'll copy this real quick and bring that down there. Sort of. Just to kind of clarify a little bit more that I'm sure you would have no problem realizing that. But so this is the neither. Now we're going to find the angle between them. So let's see. We got to do the two magnitudes. That's easy enough. Square these, you'll get 4 plus 9 plus 25, which is 38. You get 1, you square, you'll get 49 plus 1 plus 16 will be 66. So it's cosine inverse of negative 9 over those two radicals multiplied together. And I get 100.35 degrees. Yeah, this one looks a little better than that other picture, I think. At least it does to me. You can see it's a little more than 90 degrees apart from each other. And obviously you're not responsible for graphing these. Just fun to let the Maple software do it so we can take a look at it. Now let's talk about something called direction cosines. Direction cosines for a space vector are specific angles they form with each of the axes. In other words, it's an angle with respect to an axis. So there's 3 separate ones. So once you kind of get used to what this is, it's not difficult. Well, you're just kind of plugging it into a formula here anyway. But so here's your vector v. So you see it kind of comes up, and you see where it would be hitting on the xy plane if we brought it down, straight down that way. Now the first direction cosine, actually we're finding the angle. So in other words, essentially cosine of alpha equals this ratio right here. So I've already simplified it and made it, what we really want is the angles, which come from the direction cosines. So alpha is the angle formed from the x-axis, the positive x-axis. You see it brought down here, so it would be the angle coming around this way, like so. That's your alpha value, your first direction cosine. The second one is the angle formed from the y-axis, which I guess if you brought it down here, you look at it this way, it goes up like that. That's your beta. And the last one, which I believe is gamma, could be wrong on the Greek letter, it's the angle measured downward from the z-axis, like so, like that. All right. Easy calculations. Alpha is inverse cosine of your v1 component of your vector divided by the magnitude of the vector. Beta is the inverse cosine of the v2, the second component of your vector, divided by the magnitude. And then gamma is cosine inverse of the third component, v3, over the magnitude of that vector. So let's take a look at this one. So yeah, so the terminology behind this, the name is direction cosine. But you can see what we want are the actual direction angles. So here's a vector, -2, 6, and 1. We're going to find each of the direction values. So the magnitude is the square root of 41. So the first one is cosine inverse of this first component, -2, divided by square root of 41. That ends up of roughly about 108.2 degrees. The next one would be cosine inverse beta 6 of square root of 41, roughly 20.44. And the last one is 1 divided by square root of 41, and you get 81.02. Now that I'm going to, obviously if you're doing this, you're just going to have to, assume that you do it correctly. But I wanted to, use Maple to graph to let you look at our result there a little bit. It's kind of hard to tell, at least for you're going to have to, it visually may be hard to tell. It might not be that hard to tell, but you're going to have to realize that this vector is on the other side of the y-axis. It's kind of hard to tell how you look at it. It's almost like I probably should post about 5 different views of these. But anyway, because it does wrap around and it goes beyond the y-axis, that's why it's 108.2 degrees. And you can see it's not real far above the y-axis, so I like the 20.4 answer that we have. And then it's coming down 81 degrees from the z-axis, which that looks reasonable. Might not look like that much of an angle, but the problem, like I said, it's almost like you need to look at different views on this. If I turned it a certain way, it would look like more of an angle coming down from the z-axis. It looked closer to 81. So keep in mind, don't think these are the two angles coming from the same place. That's what makes it hard to visualize in 3D. So it's not like these two results are supposed to sum up to 90 degrees. That's not correct. It's kind of tricky visually, but easy calculation. That's all you have to worry about. Or maybe a few more views would help, I guess. But projection and vector components. All right. Well, I like this picture of the fellow on the boat here. I think I saw a boat picture somewhere, maybe in the book or something on the boat, but I like this one a lot better. Now, obviously, this has a lot of physics type applications here, so which we're not going to get too deep into that, but we're going to just look at the math of it. But anyway, because it's resolving forces and things like that, so that's where this has physics on, applications. So let's say you got this boat coming along this vector v, and you got a gravitational force pulling straight down on that. Doesn't have to be called vector F, but that's what we're using here. Now, suppose we're trying to break down vector F into two component vectors, W1 and W2. You remember we talked about before in another video of adding vectors. So in other words, this W2 is perpendicular to your V, and then W1 is perpendicular to that, and which means W1 is parallel to V. So ultimately, we're trying to break this vector f, which we're going to use u whenever we use the formula here, not f, to find what resistance or what vector, breaking that vector f down into this w1 vector parallel to that vector v. In other words, maybe that would give you then what the force working against the boat is in the opposite of the direction it's actually going, taking the gravitational force and applying it opposite to the direction that the boat is moving. Anyway, so the vector f here would be w1 plus w2. So what we're doing is we're taking this vector u, in theory, and we're projecting it onto vector v, where it would have two components. w1 plus w2 will equal u, but then w1 is the component part of u that goes along the same direction as v. We're projecting that onto vector v. So in other words, this projection of u onto v is going to be some vector multiple of v, because it's parallel to it, so it's going to be some multiple of it. It's a little confusing, but it's not hard to figure out. So u and v are going to be non-zero vectors, and u will equal w1 plus w2, where w1 is parallel to v. Now, of course, it could be going the opposite direction of v, sort of like the boat example up here. Remember, any multiple, scalar multiple, negative or positive, is still parallel. And w2 would be orthogonal to vector v. All right. So this notation-wise, the projection of u onto v is given by this formula. Well, the formula is right below, but the notation is projection. That's kind of weird. It uses subscript v, and here's the vector u. So whenever it's written like this, that means the bigger letter, in this case the u, is being projected onto v. It is possible that you could reverse this situation. You could take that formula and rearrange it, and you could project v onto u if you wanted to. But that's how you can tell just by notation. The bigger letter u goes onto that subscript v. So the v is what's being projected onto. But theoretically, you could project anything onto anything. Now, of course, well, that's how you find w1. U will be a given vector. And then once you find w1, if you want to know what w2 was, you don't need a fancy formula for that. It would just be simple algebra. You would just take u minus w1, which is telling you right here, and that's going to leave you w2. And that's the vector component of u that's orthogonal to v. Now here's the formula. And it's true for, plane or space. The projection of u onto v is u dot v over the magnitude of v squared times v. So what you have here, everything in these parentheses will be a scalar. U dot v is a scalar, so it's a multiple. The magnitude squared is a scalar, so it's going to be the multiple times your vector v. So the answer is going to be a vector because it's a scalar times a vector. So you will get a vector answer. Then, of course, it's telling you how to get w2, which we just talked about. So theoretically here, if you reverse this and we're doing v onto u, what you would do is you would just reverse it in the formula right here. Everywhere you see a v, you would replace it with u and vice versa. But if that wouldn't affect the numerator, it'd still be, v, in other words, v dot u and u dot v are the same thing. But you would have the magnitude of u squared here, and then you would have vector u on the outside. I'm not sure if that's really going to come up anywhere, but just in case. So we're going to find the projection of u onto v, and then the vector component of u orthogonal to v. So really all you have to do is kind of plug it into the formula. So here are our two vectors for u and v. So obviously we need the dot product. So 8 times 2 is 16. 2 times 1 is 2. 0 times negative 1 is 0. We get 18. And here we only need the magnitude of v. So it's 2 squared plus 1 squared plus 1 squared, negative 1 squared, is the square root of 6. So W1, which is the projection of u onto v, will be that dot product 18 divided by the square root of 6 squared. This just happens to be, don't always expect that to be a whole number. It's quite often a fraction. Let's see, so it just ends up being 18 over 6, so it's 3 times vector v. So it's 3 times 2, 1, negative 1, which gives us 6, 3, negative 3. Now to find W2, you just take your vector u right here, 8, 2, 0, and you subtract off that W1 we found right there. And so you have 8 minus 6 is 2, 2 minus 3 is negative 1, 0 minus a minus 3 is plus 3, and there we go. Now one thing you could check if you want to, it's not mandatory, but just to double check, since W1 and W2 they are orthogonal to each other, you could do a quick dot product on these two results right there and make sure they equal 0. Because if they did not dot to be 0, that means you either have W1 wrong or W2 or both. So I'll just check that real quick. 6 times 2 is 12. 3 times negative 1 is negative 3. Negative 3 times 3 is negative 9. So 12 minus 3 minus 9 is 0. So W1 dot W2 equals 0. So that's just because it doesn't take long to do it. Not a bad idea to check that. And all right, well here's a little, maple sketch of all these vectors. So here's u, the big red one. V is the blue one. So you see, u is being dumped down onto v to make W1. So it's kind of hard to tell from this picture, but kind of use your imagination because, vectors can move around. They're all starting from the origin, which kind of makes sense. But W2, it could move down here, and W2 would actually fit right here, right there. And it's hard to tell, but it would be a 90-degree fit there. But W2 would come in right there, and W1 then plus W2 would equal u. So here's u slapped down onto there. So the W1 part of u, you see, is bigger than v. Yeah, it's actually 3 times v. We just figured that out a minute ago. So there's u projected onto v and gives you W1, which is running right along with v. Excellent. And I was mentioning this a minute ago. I mean, I wouldn't worry about this unless you have to, but I just showed, if I wanted to go v onto u, I just switched all the letters around. That's all you'd have to do. I don't think I graphed that one, did I? That might have been interesting to look at. So this time it would have been taking v and putting it on the blue v onto the direction of u. But you can see, and I won't go through all the details here, but you can see that v being projected onto u is going to be a smaller vector than u, isn't it? It's going to be shorter. So this multiple that we get from this inside part is going to be a fraction less than 1 because it's smaller. Let's see if that worked out right. Yeah, so it was 18 over 68, which reduces to 9 over 34, and then it reduced again. But yeah, so basically it's, okay, 9 over 36 is 1/4. So I'm going to say it's a little bit bigger than 1/4. Let's see how that looks according to the picture. Yeah, so that if you brought this up and over here, it'd be a little more than 1/4 along the way to u. And here's another. All right, what do we have here? Two vectors u and v. Now, see, a lot of times I've mentioned this in another video about space vectors. So this is standard unit vector form. So I just immediately converted it over to component form. So there's no j for the first one, no j for the second one. So 1/4 I plus 4k is 1/0 4, And then 3i plus 2k would be 302. And just plug it right into the formula. U dot v, 3 times 1, 4 times 2 is 11. Magnitude of v is square root of 13. So you have 11 over the square root of 13 squared. So it's 11 over 13. So u projected onto v would just be the multiple 11 over 13 times vector v right there. So 11 over 13 times vector v would give you 33 over 13, comma 0, comma 22 over 13. And then W2, the vector component orthogonal, would just be u minus that W1 we just calculated. So u is 104. We subtract out this vector, and then we get negative 20 over 13, comma 0, comma 30 over 13. And as I mentioned before, I'm not going to worry about doing it here, but if you wanted to do the dot products, just dot product to see if it's 0, to check there's nothing wrong with that. One little trick, and I think we'll probably use this again later if I remember correctly, but when you're checking dot products, you can factor out a scalar multiple of 1 over 13 over here and 1 over 13 here, because if the rest of it dots to be 0, even with a scalar multiple on the outside, it's going to be something times 0, so it's still going to be 0. So just to show you, I can skip the 13s, and I can go 33 times negative 20 is negative 660. 22 times 30 is positive 660. Add those together, you get 0. It would not matter those 13s on the bottom, because it's still going to be 0. Okay, just thought I'd mention that. Oh, I don't know. I just thought I found this problem in the book. Thought I'd do a quick little work problem here. Should have copied the problem out of the book. As you can see from my diagram with a little teddy bear in the wagon. I do not have an advanced degree in art studies, or art period. Well, that's okay. So this kind of has a fancy formula here, but really it's just a dot product. It's your force times your distance. Now back in Cal 2, we're assuming constant force. Cal 2, we looked at the integration formula. It's an integral whenever the force isn't constant. So, all right, these units are foot-pounds, so it's 25 pounds being applied at 20 degrees. So what you need to break it down into the vector of what the vector would represent in its two components. So the x component would be 25 cos 20. The y would be 25 sine 20. And if you're going 50 feet horizontally, that vector would just be 50, comma 0. So you just do a dot product and you get roughly 1174.6 foot-pounds. Ta-da! And that concludes the video for the dot product.